Namaste bachon, welcome to the class. Today we're going to tackle a very important topic from Unit 3, Current Electricity. We're talking about electric currents in conductors. Now I know this part can be a little confusing, but I promise you by the end of this session it will be absolutely crystal clear. And most importantly, we learn it in a way that is completely exam safe, so you don't lose a single mark.
So let me start with a question for you. Have you ever wondered about this? You flick a switch and a light bulb, maybe even in the next room, it turns on instantly. But here's the crazy part. The electrons that make up the current, they actually move incredibly slowly. Even slower than a snail. So how is that possible? This is the big mystery we are going to solve together today.
So here's our game plan. First, we'll tackle that light bulb mystery head-on. Then we'll imagine a dance floor full of electrons to really see what's happening inside a wire. After that, we'll get the proper exam-safe definition of current. We'll solve the mystery for good, bust some common myths that make students lose marks, and finally, we'll summarize everything. Jello, let's begin. Okay, Section 2, a dance floor of electrons. To really understand current, we need to picture what the electrons are actually doing inside a metal wire, and this analogy is going to make it super easy.
So look, inside a normal piece of wire, one that's not connected to a battery, there are billions and billions of free electrons. And they are not just sitting still. Oh no, they are whizzing around randomly at unbelievable speeds. We're talking about 1,000,000 meters per second. Just imagine a very crowded dance floor where everyone is just jumping and jigging around randomly in their own little space. There's a lot of motion, right? But the dance floor as a whole isn't going anywhere. The net movement is zero. For every electron going right, another one is going left. Tika? Now, what happens the moment we connect a battery? The battery sets up an electric field inside that wire, almost instantly, from one end to the other. Now, going back to our dance floor analogy, this is like tilting the entire floor, just a tiny bit, creating a very gentle slope. So, what do you think happens to our dancers now? Well, they continue their super fast, random jumping and jigging. But because of that tiny tilt, every dancer also starts to slowly drift downhill, all together in one direction. This very slow, coordinated movement is what we call drift. And bacho, this tiny, slow drift of billions of electrons, that is what we call electric current. So remember this, there are two motions happening at the same time, the very fast random one and the very slow, coordinated drift.
Right, on to Section 3, the real definition of current. Now, please pay close attention. This is the exam-safe part. This is what you need to write in your papers to get full marks.
So, what is electric current, which we represent with the symbol I? According to the textbook, it is defined as the rate of flow of electric charge. It's that simple. It is not about how fast the charge moves, but all about how much charge passes a certain point in a certain amount of time. The formula, as you know, is I equals Q divided by T, where Q is the total charge and T is the time. And of course, the unit is the ampere, symbol A.
Now, let's get to the really interesting part. Let's connect this big idea of current that we can measure to the tiny world of electrons. For this, we have the microscopic formula I equals NEAV sub D. Don't worry, it's simple. Here, N is the number of free electrons in a unit volume, basically how crowded the dance floor is. E is the charge of one electron, a constant. A is the cross-sectional area of the wire, how wide the dance floor is, and V sub D, that's our hero, the slow drift velocity we just talked about. See? This one beautiful formula links the big current to the tiny drift velocity V sub D.
Okay, Section 4, solving the mystery. So we know the drift is slow, but why is it so slow? Let's take a closer look and understand how this drift velocity actually works.
I want you to imagine the journey of just one electron. First, the electric field from the battery gives it a small, constant push, a force. Because of this force, the electron starts to accelerate. But it can't go far. Very quickly, bang, it collides with one of the fixed ions in the metal structure. In that collision, it loses its momentum and almost stops. But the field is still there, right? So the whole cycle starts again. It gets a push, it accelerates, it collides. Push, accelerate, collide. This happens billions and billions of times every single second.
Now, this constant start-stop motion means that on average, the electron only moves forward very slowly, but just how slow is slow? You know what? Let's actually calculate it. Let's find out the drift speed for electrons in a normal copper wire carrying a pretty standard current of 1 ampere. To do this, we just take our microscopic formula and rearrange it to find V sub D.
So V sub D equals I divided by N times E times A. Now the most important number here is N, the electron density. For a good conductor like copper, this number is it's mind-bogglingly huge. It's about 8.5 into 10 to the power of 28 free electrons in every single cubic meter. It's literally a sea of electrons.
And when we put all the values into our formula and press equals, the drift velocity comes out to be about 0.074 millimeters per second. I mean, just think about that. That is less than 1/10 of a millimeter every second. So now we are back to our original mystery. If the electrons are moving this slowly, why does the bulb light up instantly? And here, finally, is the answer. The individual electrons don't have to travel all the way from the switch to the bulb. No, the electric field, the start moving signal, that signal travels through the wire at nearly the speed of light. It tells all the electrons in the entire circuit to start drifting at the exact same time. So the electron right next to your switch starts to drift, and at that very same instant, the electron that is already inside the bulb's filament also starts to drift. And that's why the effect is instantaneous.
Okay, let's move to a very crucial section. Section 5, Busting Common Exam Myths. Please listen very, very carefully. These are the silent killers, the common mistakes that can cost you precious marks in your exams. First big myth. So many students write in their papers that current is the speed of electrons. This is completely 100% wrong. You must remember, current is the rate of flow. It measures how many charges cross a point every second, not how fast each one is moving. Think of traffic on a highway. The current of traffic is measured in cars per minute passing a toll booth, not the speed of each car on the speedometer. And the second myth is the one we've just busted, that slow electrons must mean a slow effect. This is also wrong. Remember, the signal to move, that is the electric field, travels at almost the speed of light. It's like a long line of dominoes. You push the first one, and the last one, far away, falls almost instantly, even though each individual domino only moved a tiny little bit. The signal is fast, not the domino. All right, we're almost at the end. Section 6, Summary and What's Next. Let's quickly connect the dots and see why understanding this idea so well is really, really important.
You see, understanding this microscopic picture of current, this idea of electrons drifting and colliding, it is the key that unlocks the rest of this chapter. It is the fundamental basis for understanding Ohm's law. It helps us understand resistivity, which is why copper is a good conductor and what is not. And it's essential for calculating electrical power and the heating effect of current. All of these big, important ideas are built on this one simple concept of electron drift.
So here are the key takeaways for your exam. Please, if you can, make a note of these points. First, current is the rate of charge flow, I equals Q by T. Second, this current is caused by the slow drift of countless electrons. Third, this slow drift is just a tiny motion on top of a much, much faster random thermal motion. Fourth, the electrical effect is fast because the signal, the electric field, is fast. And finally, you must remember the microscopic formula that connects everything. I equals NEA V sub D.
And I'll leave you with a final thought to ponder over. We have established that the drift of electrons is incredibly slow. So here's a question. How is high-frequency AC, or alternating current, even possible? You know, in AC, the electrons have to move back and forth, sometimes 50 times every second. How can they possibly do that if their net movement is slower than a snail? Think about it, and we will explore this puzzle in our upcoming explainers. That's all for today, Butcho. Study well.